Hello, grade 11s. Today I want to talk about our next group of hydrocarbons. I want to talk about benzene. Benzene is still a hydrocarbon. There's only hydrogen and carbon present in the molecule, but this is a very different looking molecule. You notice that it forms a big ring structure? We have 6 carbons present in this ring and 6 hydrogens attached to them. It's also really important for you to notice that every other bond is a double bond. This way, every carbon has its requisite 4 bonds. Remember, 4 being the magic number in chemistry that every carbon has to have. Now, these bonds actually have some resonance. They actually tend to bounce back and forth. So even though right now it looks like the double bonds are between these 2 carbons and then these 2, it's possible that they could also shift positions one over. Kekule was a scientist who came up with some shorthand drawings for benzene. So these drawings that we see here are Kekule structures for the benzene molecule, where each corner represents a carbon. The double bonds show where they could be, and you can notice that sometimes they're in one position and sometimes they're in the other. Because these double bond positions can switch back and forth so regularly, we often will instead put just a circle in the middle to represent that. Now, it's important that we don't just draw a 6-sided ring. By the way, when I draw these, I think of this little house and a roof on the bottom. But this here is not benzene. This is cyclohexane. In this particular shorthand drawing, the carbons are still in the corners, but you're noticing only single bonds. This molecule, if I were to draw it in a more conventional fashion, would require 2 hydrogens branching off every carbon and is not benzene. So when you draw the shorthand version for benzene, I want you to remember to either use alternating double bonds or to put a ring in the center. Now, typically for benzene molecules, when we do this kind of a thing, we will draw them using the shorthand. You'll almost never see me draw the entire molecule out like this. But as I explain the different types of bonding structures, I will draw them out for you like that so you can see where the bonds are. But even in a full structural diagram, it is considered acceptable to use the shorthand for the benzene portion of the molecule. Now, since there's only 1 hydrogen branching off each of these carbons, this is the most likely place for branches to occur. The ring itself is incredibly stable and almost never breaks, but we can knock the hydrogens off and replace them with all kinds of different molecules. Benzenes are considered the aromatics of the hydrocarbons. We've already done the alkanes, where we had single bonds between every carbon, the alkenes, where there was at least 1 double bond, and the alkynes with the triple bond. But this is where benzene happens. Benzene is called aromatic because it's smelly. It has an aroma to it. Also, those alternating double bonds, that resonance pattern in there, is also referred to as aromaticity in terms of chemistry. But benzene molecules, we'll notice, are always very smelly type of molecules. Now, one of the most common things that can happen is we can pop off hydrogens and replace them with branches. There is a whole group of di-substituted benzenes. Di meaning 2. Substituted meaning I've taken off the hydrogens and replaced them with something else. I'm going to use the simplest thing we can replace them with. We're going to replace with methyl groups. Meth meaning 1 carbon, YL meaning that they are branches. And di-substituted benzenes, where we substitute 2 hydrogens, are really common. And because they're common, they've given us some shorthand for naming them. So here we have a benzene structure, and we can see here's my benzene structure, and we have 2 branches. We have 1 here, 1 here. So this is 1,2-dimethylbenzene. When I number this, I have to give lowest numbering rules. So this is carbons 1 and 2 of the 6-carbon benzene ring. Now, I could have numbered it in the opposite direction as well. It doesn't matter so long as I put the lowest numbering in the name. But positions 1 and 2 can be substituted by the Greek letter ortho. Ortho means positions 1 and 2. And because it's standing in for numbers, we treat it like a number and use the dash. This is orthodimethylbenzene. Now, dimethylbenzenes have a common name called xylenes that existed before the UPAC rules came into place. So you might also see this labeled as orthoxylene. This is a more common way that I would draw a skeleton for orthodimethylbenzene. We can see that the two methyl branches are positions 1 and 2. What if there's a space between them? Well, now my branches are positions 1 and 3. So if I call this carbon 1, carbon 2, carbon 3, and number in this direction, I could have also called this 1, 2, 3 as well. Again, it doesn't matter so long as we get the lowest numbering. This is 1,3-dimethylbenzene, or meta. Meta-dimethylbenzene will go M-dimethylbenzene with a dash because the meta is standing in for two numbers. Now there is one more spacing that is possible. This is when the two branches are exactly opposite of each other. This is considered the para position. Positions 1 and 4 are the para positions. So we have 1,4-dimethylbenzene or para-dimethylbenzene. So you can use either of the two terms when you name a structure. It's both considered correct. But I do need you to be able to recognize the shorthand version and understand what it means in terms of the numbering. Now, obviously, we can't get positions 1 and 5. If I then, again, draw you a very quick benzene structure, and I try to go position 1, 2, 3, 4, 5, this actually isn't positions 5. In this case, it makes more sense to number in this direction. And again, I can start here or here, and just to be silly, I'm going to start at the bottom one. This is still positions 1 and 3. Remember, it makes no sense or no difference which place you choose to start numbering from so long as you get the lowest numbering. So this is still positions 1 and 3. There are two methyls on a benzene ring. So this is 1,3-dimethylbenzene. Or positions 1 and 3, again, is meta-dimethylbenzene. So we can use any of these numberings. Now, it can also use them if the two branches are different from each other. That's also considered acceptable. Again, starting with a benzene ring. Suppose I put a methyl branch here and a propyl branch here. I can still use the shorthand numbering. I have a choice to name my branches in terms of alphabetical order, or I can name them in terms of complexity order. Since M comes before P in the alphabet, I would name methyl before propyl. But also, methyl is smaller than propyl, so alphabetical order or complexity order says that the methyl branch has to be named first. So because it has to be named first, and I've got no choice in the matter, I'm more likely to call this carbon 1, carbon 2, carbon 3. Carbons 1 and 3, again, is the meta position. So this could be meta, methyl, propyl, benzene. We could also call it 1,3-methylpropylbenzene. It would not be correct to put the propyl before the methyl in this case because it violates the two possible orders that we can list our branches in. Now, we only use this shorthand, the ortho-meta-para shorthand, if we have two substitutions. We wouldn't use it otherwise. So, what are the rules for naming benzene structures? Well, sometimes we name it benzene. Sometimes we can treat benzene as a branch. And when it's treated as a branch, we call it something different. How do I know when to treat it as a parent and when to treat it as a branch? Well, when benzene is attached to carbon 1, okay, of an alkane, so benzene is our parent chain if it's on the end carbon of an alkane. In this case, we've got benzene attached to carbon 1 of a methyl, so I would treat this as benzene the parent and methyl the branch. It is methylbenzene. It's more correct to call it 1-methylbenzene, but because there's only one branch and there's no other place to put up a carbon 1, it's considered acceptable to drop the numbering in this case. Methylbenzene has a common name. It's called toluene, and that is such a common name that the curriculum guide has us wanting to have it memorized for our understanding. In this case, in our second case, we're still attached to carbon 1 of this very long hexane chain. So again, I'm going to treat benzene as my parent, and the hexane, now hexyl, because it's a branch, is my branch. And this is hexylbenzene, or if you want to be very correct, 1-hexylbenzene. Here's another case below where I have a benzene on a hexane, but now we're attached to the middle of the branch. In this case, when we are attached somewhere in the middle, one of the central carbons, I cannot call benzene the parent. Benzene is now my substituent, or my branch, and as a substituent, it's called phenyl. We spell it YL because that tells us it is a branch. We say this phenol to distinguish it from another structure that we'll learn, phenol, which is very, very close in spelling. It's spelled OL, but that's an alcohol. So phenol, PH, or I guess if I want to be really proper with my phonetics, I would say phenol, is how we pronounce this as a branch. In this case, like I said, we're going to highlight. I will call this my parent. It is hexane. The phenyl is my branch, and it is attached to carbon number 3. We number in this direction to give it the lowest possible numbering as a branch, because on an alkane, the branches get the lowest number. Phenylhexane. Here's another case where we have my benzene on carbon 1. That looks good, but if I tried to name this as a benzene, then I would somehow have to name this whole thing as a branch because it's coming off of just one point. And we don't know how to name a branched branch. That gets very difficult. So in this case, again, I am much more likely to pick up my highlighter and call butane my parent. On my butane chain, there are 2 branches. There's a phenyl branch and a methyl branch. Remember, we have alphabetical order or complexity. In both cases, that tells us that the methyl has to come before the phenyl in the name. Now, I know that it feels like, but phenyl's on carbon 1. Naming in the order you see them is not one of our allowed rules. It's alphabetical order or complexity order. Sorry, but they didn't invite me to the party where they made these rules. So those are the ones we have to play with. My numbering, however, will go in this direction to get the lowest numbers to the parent chain. And so I've got my methyl on carbon 3 and my phenyl on carbon 1. What I'm hoping you're able to do now is that you can draw structures that involve benzene rings and you can name them. That you'll recognize the use of the words ortho, meta, and para when we have disubstituted benzenes. And you know when to call the chain benzene when it's a parent chain and when to call the chain phenyl when you want to call it one of the branches. There is lots of practice on naming and drawing benzene structures on pages 27 to 33 of your green workbooklets.